Our project is Gaganyaan H1 mission is mainly about communication system used in India's Gaganyaan mission. Before going into the project, we have to understand the purpose of Gaganyaan. Gaganyaan is India's first manned space mission, so maintaining communication with astronauts is very important throughout the mission. The spacecraft will travel in low Earth orbit at a speed of nearly 27,000 km per hour and completes one revolution around Earth in about 90 to 120 minutes. Since it is a 3-day mission, the astronauts may orbit Earth around 48 times. We use low Earth orbit because it is closer to Earth, needs less launch energy, and gives better communication with less delay. Now, unlike unmanned missions which are controlled automatically without humans inside, Gaganyaan carries astronauts, so we can't afford communication loss even for a short time. That's why systems like IDRSs become very important. And these are the unmanned missions which were successfully conducted by ISRO, and these are the upcoming manned missions. And at 26 TVA1, TVA2. IDRSS stands for Indian Data Relay Satellite System. It consists of two satellites, IDRSS-1 and IDRSS-2, developed by ISRO. These satellites help in continuous communication between spacecraft and mission control. They send telemetry, tracking and command data, and also reduce the dependence on ground stations alone. Both satellites work together, and if one satellite is blocked or temporarily unavailable, the other provides backup communication for safety. Project overview. So in our project we use MATLAB to simulate this complete communication network. In this simulation, we can observe the movement of Gaganyaan in low Earth orbital, the positioning of IDRSS satellites, and how communication links are maintained with mission control through satellites and ground station during the mission.
So this is how the simulation
And here is the
like.
coding part for the simulation.
You can see there's IDRSS 1 and 2 in reachable angles with the ISRO. There's ISS and Gaganyaan revolving around Earth in LEO orbit in different angles and phase. The IDRSS will communicate with the Gaganyaan covering most of the revolution time. ISS will communicate with Gaganyaan throughout, as we can't risk communication with actual people in space. Thus, ISS moves in slight offset to communicate with IDRSS even when the Gaganyaan is out of reach. We have two space stations in the other side of the globe, Brazil and Ushuaia, to be sure that we can communicate with the astronauts throughout. There's a link between ISRO, Gaganyaan, and ISS when it is on top of Bangalore. You can see it when it's on top. There you go. The yellow line will show the link. The IDRSs can communicate within themselves and with ISRO throughout. I have differentiated the links with different colors. We have simulated two full revolutions of Gaganyaan around Earth.
After simulating the communication network, we also analyzed different parameters that affect satellite communication during the mission. First is Doppler shift. Since the spacecraft is moving at very high speed in low Earth orbit, the signal frequency keeps changing. When Gaganyaan moves towards the receiver, the frequency increases, and when it moves away, the frequency decreases. So in our simulation, we can observe how the Doppler shift changes during the revolution and how the system adjusts to maintain stable communication. And next is free space path loss, which is basically the weakening of the system as it travels through space. As the distance between the satellite and ground station increases, the signal spreads out and becomes weaker. So we analyzed how Gaganyaan experiences signal loss during the communication and why higher antenna gain or transmission power becomes important. We also studied range rate, which tells how fast the distance between two communicating objects changes. This is important because it directly affects Doppler shift and also helps in accurate satellite tracking. Another important parameter is energy per bit by noise power, which represents signal quality compared to noise. A higher energy per bit noise power ratio means the received signal is cleaner and the chance of data errors are lower. Along with that, we analyzed carrier noise power ratio, which measures carrier signal strength compared to background noise and helps determine whether the receiver can properly log onto the signal. Then we looked at link margin, which acts like a safety buffer in communication. If expected interference or atmospheric effects weaken the signal, a positive link margin helps maintain the communication link without interruption. Finally, we also considered atmospheric effects like atmospheric absorption and ionospheric scintillation. Ionospheric absorption causes signal attenuation because gases like oxygen and water vapor absorb part of the radio signal. Ionosphere scintillation causes rapid signal fluctuation due to irregularities in the ionosphere, especially near the equator. Since India is the near equatorial region, this becomes an important factor in satellite communication analysis.
We have analyzed the parameters and plotted real-time graph for them. These are the Doppler shift, range rate, link budget, and atmospheric absorption. And these are the free space path loss, EB by N naught, carrier to noise density, and ionospheric scintillation. The graphs are real time, thus they show the actual parameter values for every analog position of satellite around Earth. It shows the communication loss and affecting parameters between Gaganyaan and ISRO communication as a whole.
And here are the separate graphs for each analyzed parameters. So overall, our project not only simulates the communication network of Gaganyaan, but also analyzes how different real-world factors affect communication reliability during the mission.